Welcome back. We are now going to have an open discussion with the daily speakers, so Laszlo, Rachwał, and Modesto, and you're welcome to ask as many questions as you want. So, is there any question? Richard.
So I'll ask it to either of the two speakers, the question that I warned Leonardo I was going to ask, although either of you can answer it. And that is, I'm really concerned about the classical limit because all of our low energy data is coming from classical gravitation. We've never seen low energy quantum gravitational effects. And I'm worried about whether all the tinkering that you do to get the ultraviolet to work out puts that at danger, at risk. So to make my issue concrete, I've already asked you about what the classical limit looks like. To make my question concrete, suppose that we're dealing with a hard-headed numerical gravity person. He's somebody who's he's trying to work out a LIGO signature, and he's somebody who discretizes space-time, and he says, okay, look, one derivative is 1 time step forward, 2 derivatives is 2 time step forwards. If you give me something like e to the box, what sense am I supposed to make out of that? How do I numerically simulate that?
Well, so in the non-local case, the classical action is what I showed during the presentation. Where is the pencil? So the classical action is defined from the beginning. No, the decay ddx. A to the h box minus 1 box r mu nu. So of course the DM formulation here is not that trivial and basically useless. Okay. However, this is the classical action. And my point of view, or at least what I'm able to, let me finish, what I'm able to do to the end.
He could vary it. Then he gets a set of equations.
Yeah, you get some equations so much. You vary your action and respect to the metric, and you get some equations of motion, which are g mu nu plus order Ricci square. This is the variation.
Particular things involving e to the box. And then this
No, it's here. Everything's here. It's very important. It's very important. This shape of the question of motion is very important. You know why? Because as I said, ADM formulation is something that is not really under control at the moment. So forget this for a moment. However, So however, I of course can write down the questions of motion, which are quite involved, but you can find in many papers, also by Koshlev and others. And what is the nice peculiarity of this equation of motion is that if r mu nu or g mu nu is equal to 0, then also e mu nu is equal to 0. All the solutions you know about Einstein equations are solutions of this theory, exact solutions. Of course, it's not true the other implication. There are other solutions that maybe there are, there are. I have an example at least, but I'm not sure in genius. I have an example in let me say yeah. Yeah. In principle, you can have infinite many solutions. Okay. So however, from coming back to your initial question about observations. So what we observed till now is for sure these solutions, right? And
excuse me, the numerical gravity guy would say he's looking at a source, so g mu nu is not equal to 0. There's
okay, one step at a time. So let's start with vacuum. Then later I will come to the second point. So just one more comment about exact solutions. So we have these exact solutions. Moreover, all the equation of motion for the perturbations take any background solution of these equations of motion that are also solutions of e mu nu. So e mu nu of g bar is equal to 0 plus a perturbative expansion epsilon n hn, which means perturbations of the Einstein equations. The equation of motion for the perturbations are again of this theory are again the same of Einstein's theory. So the stability analysis is exactly the same of Einstein's theory at any perturbative order. That's great. No, please tell me that is great. So after, let me complete this part. So this is in vacuum. But that's only the beginning of the story, because afterwards we proved that we can construct another theory which includes even matter. In other words, here you have the classical, let me call this epsilon or capital epsilon. So you can include even matter, and these are the Einstein equations including matter now. Instead of G mu nu, you have E mu nu. So you have also your energy momentum tensor plus L matter now, you have to add. And in this class of theories that are finite, supernormalized, but whatever, all these nice properties, unitary, you have exactly all the same solutions of Einstein's theory, including matter. Therefore, you can study now the problem, the numerical problem, just for this equation, and you again get the same numerical results of Einstein's theory at a classical level.
Look, I'm sorry, do that variation in my head enough to see that what you're saying is just not true. It looks like if I plug in G bar mu nu or if I plug in full G mu nu is equal to G bar, which is a solution of Einstein equation. It has ρg equal to 0 plus H mu nu. I'm going to get some terms both in the G mu nu part and the R mu nu part and in the E to the.
Yeah, but this one is always one order higher.
So what?
So in perturbative, so all the so at the order epsilon to 0, you have a G bar, right?
All you're doing is
at order epsilon 1, you have
is a solution. That isn't a proof that.
No, you have an equation of motion at any perturbative order. You have an equation of motion which will be your equation of motion at the order epsilon.
But any extra solution, that's what you can say.
No, if you start from the background solution, which is solutions of Einstein equations.
Okay, that's
Yeah.
All you're doing is.
Okay, there are other solutions, other perturbations, other instabilities. That's another story. Yeah.
I think this is not the equations of motion. Let's suppose that your E mu nu is e to the box G mu nu.
E mu nu is
An answer for E mu nu. Your equation is e to the box.
this one.
Right, E mu nu equals e to the box G mu.
E to the box G mu nu.
So something that factorizes G mu nu when G mu nu is 0, not is 0. Would you say that this is extra solution?
No.
I would say no. Yes.
Okay.
And I think that your case is something like this.
Exactly.
Let me give you an example. Suppose we start with point particle theory. So no general relativity, simple point particle theory. We have it be the harmonic oscillator of a one-dimensional point particle. Harmonic oscillator plus a term that involves higher derivatives. Let's have it be a coupling constant G times Q double dot to the third power. Exactly what you're saying will be true.
It depends on how you so suppose you have your what is the action? So you have a Lagrangian which is 1/2 d tau x square, right?
Q squared.
You have this plus omega square x square, right? This is your classical equation, your classical Lagrange.
Put a minus sign.
Okay, doesn't matter. So this is
Minus sign in the second.
this I call L local. Okay. Then I use my recipe. My recipe is L local plus E local, a fourth factor, which is an entire function, E local. Okay, for this theory. Then what I said is true even for this. Of course, it's not true for any theory, but if this is the recipe, so this is my non-local harmonic oscillator.
But you're just ignoring solutions that exist that are perfectly good solutions of the theory.
Fine, there are other but I'm not ignoring the harmonic oscillator solution, the one that everybody is familiar with. So the solution The solution x equal a cosine plus b sine is exact solution of this theory too, and all perturbative perturbations of this, which is so this is x0 plus delta x. All the equations of motion for the perturbations are the same of that, which means you have the same stability problem.
If I write down that ansatz, if I stuff that into the equations of motion, I will get some things that involve fourth derivatives of x double dot, right?
But they are exactly zero because the equations of motion of this is EL plus order EL square equals 0. So if EL is 0, this is 0, this is 0.
Make it be so that there will not be equal to 0. Let's see, you've got an EL on both sides of the thing. That's not what you're doing here at gravity.
No, it's the same. It's exactly the same.
No, you've got G mu nu and R, or G mu nu and R, where it's G mu nu equals 0 is the equation of motion. Suppose I do it.
No, okay. G mu nu is equal 0 is if you take a solution such that G mu nu is equal 0, then epsilon mu nu is equal 0. There.
We have to argue about that point. I claim that there are extra solutions which will have the property that the fourth derivative, EL, will not be equal to 0 in the equation.
Yes, you can have extra solutions. Yeah, this I agree. I agree on this. You can have extra solutions, yes.
Okay, but that's the issue, right?
No, you can have extra solutions. What is the issue?
So do you claim, Richard?
Yes.
Do you claim that you always have extra solutions?
But even if, what's the problem?
That's what I agree. But take into the box G mu
Yes,
equals 0.
yes.
What are the extra solutions?
So they would be things, so you want to just put an entire function. Good, let me just be clear though. You're taking an entire function of the differential operator and acting it on the linearized Einstein equations. First, you wouldn't get that ever out of a variational principle. But even if you did, the extra solutions are ones which would have the property that they don't make sense, they don't make sense, they don't have a good Fourier transform. So e to the box acts on them, or box acts on them to give minus infinity.
No, I don't get the point. So we have a theory, right? And we have a class of solutions, exact solutions that are exactly the same of Einstein's theory. We agree on this? We also have the same equations for perturbations of Einstein's theory, which means we can claim stability or instability according to Einstein's theory, even for the non-local theory. We agree on this? We agree. I think we agree, no?
I think there are extra solutions.
No, that's the third point. This is the second point. First point, exact solutions that are exact solutions of Einstein's theory. Second point, perturbations of that solutions.
You insist on doing linearized perturbation theory that.
No, any order, of course, not infinity, but any order.
If you insist.
No. Let's clarify what's the question first. And what is the statement? First, G mu nu equal, so first G bar mu nu, which is a solution of this equation, is a solution also of the full theory. So E of G bar equals 0. Second, because of this property, also all the perturbations at any order are the same of Einstein theory. So this is equivalent to Gn.
That's not true.
No, that's true. That's true. It's a proof.
Since you already admitted that there are solutions.
No, not solutions, perturbations.
There are.
So what we do in classical?
G mu nu is equal to the G mu nu bar plus something else could be considered a perturbation. And there are solutions.
That's the definition of perturbation.
You admitted it yourself, which have the property that F acting on those things is not equal to 0.
So what is?
And it cancels the.
No, wait, again. Sorry about this. Sorry. First, let's focus on the solution, and afterwards on the stability. That's my logic. Okay. So there are solutions. No.
Perturbation theory. I agree that.
Okay. Then we are fine. We have G bar, which is an exact solution, and perturbations that are the same of Einstein's theory. So we know a lot about the theory.
Third theory.
Now we come to your part. You are worrying about other solutions.
Then I want to add something.
So why you have to worry about other solutions? So Minkowski is stable and is a solution of the theory. Is not, why is not stable? I prove here, it's written here. Richard, sorry, but it's written here. It's written here. If all the perturbations are the same of Einstein's theory, then you can resume all the theorems by Christodoulou-Kleinerman and claim stability at any perturbative order.
Okay, you disagree. Yeah, I mean, it really depends on what type of form factors you handle. And you can have perhaps extra solutions, but those of GR, they
No,
should
well,
be recovered.
in this construction does not depend even from the form factor. You need well, no, you're right. It depends on the structure. Yeah, you're right.
Did you want to add?
It's not obvious to me that you always have extra solutions.
This I don't know indeed. This I don't know.
Yeah, that is also unclear to me. Mhm. And
A solution with box equal minus infinity. I don't know that.
That is the
I don't
problem.
know what it means. Box phi equal minus infinity.
It means that the system develops a very bad time dependence, and that's the problem with those kinds of theories.
Well,
there is a
I
follow-up
don't
by
know, but the important thing is that G mu nu equals 0 is a solution.
yeah, and there is a follow-up by Benjamin, or a new point.
Hold on, sorry, I'm just trying to make sense out of your discussion. I think we agree that the zeroth order, like the equations of motion, are the same. We agree that linear perturbations are the same.
Not only linear, any order
No, look at it. Quadratic perturbations.
are the same.
No.
I can prove.
You have 3-point function and then you kill two equations
No,
of motion and it's not.
The structure is this one, right? The structure is this one. So you have E squared here. If you expand, you always get in here. You get order 1, okay, and order 2. But order 1 is already 0 because of the previous step. So this never contribute. It's in my paper. You can check. Even it's in my slides. Show me slides. If you show the slides, I can prove. I can give you the proof right now.
Probably it may, I mean, what you are saying is definitely true if you have like a cubic operators, but in this case, I think it stops at quadratic order.
The cubic can be fine as long as it reaches cube.
Exactly. But in principle, you could have something like a Goroff-Sagnotti terms, and then you
Yeah,
break
if it's Riemann, no. If it's Riemann.
Exactly. And I think this is what you meant? Or
My point is just that if you take the 3-point function of such a Lagrangian, you can and then evaluate it on the equation of motion. It doesn't match.
No, I mean, as I said, you have to retirate. What's the word? I mean, you have to start from the step 0, order 0, and then the equation of motion, the order 0 is 0. I mean, if you have the slides, it's simpler because. Okay, but it's in the slides anyway. Okay, however, you can have extra solutions. You're right. I mean, you can have for sure. I mean,
in principle,
we are
yes.
not sure. Tell me.
Depending on the form factor, right?
I mean, I'm not sure. I never found one. So
there is a follow-up by
for example, people working on regular black holes have I did also have approximate extra solutions, and not only Schwarzschild, for example, limit, but this is approximate, so it's not.
This whole discussion was apropos of my initial question was dealing with a hard-headed classical general numerical relativist. And he looks at an equation like that and he says, gosh, that seems to me to be asking for initial value data.
That's hard.
No.
That's hard.
How do I directly say that?
Yeah, Richard, maybe I try to answer your original question, although it's a trial. So I would say that, yeah, everything depends how we represent the form factor. Of course, it's an entire function, but at least there are 3 ways how we can represent, in a sense, tell how the numerical relativists could do something. So one of the very naive way would be just say, I know what's exponential, I can write a Taylor series. And when you have higher derivatives there, the only problem is, of course, it's infinite. And when you have to take the limit that in principle you should analyze not just one numerical system, but you have to analyze an infinite sequence of them and look for the behavior that arise in the limit when you go to infinity. And there is, of course, a problem that you have a lot of artifacts that you can assign to the fact that you truncated your theory to some higher derivative terms, and then you have to know how to remove these artifacts. And this is also reflected in our... Because probably, I'm not saying with full certainty, but this is also what was in the discussion, that at the end, this is not that we have always the same solution. Sometimes there could be new solutions, but also there are situations in which we can prove that the number of solutions of the initial thing and of the final after full resummation is the same. So
they're all going to be solutions, because the thing is, an entire function, it converges to its Taylor series expansion. So they're all going to be solutions. They're just, in the limit n goes to infinity, going to have properties that you don't like. And I would say that's exactly the problem.
So this is, let me just finish. So this was one way how you can, if you want really to tell to the people who do numerical simulations, of course, they will not understand what's e to the box. But if you tell them do box or box squared or box cube and then go on, although of course it takes infinite number of resources. This is another problem, but theoretically, this is how we should explain. This is one way. But the other way how we can represent the form factor, there are various integral representation. For example, e to the box has nice integral formulation using the Schwinger integral. Yeah.
And that's required to either below the future or not.
Yes.
How does the guy?
So, and this requires that you have the formulation that maybe you don't have just to do the problem with, as I said, higher derivatives, but maybe you have to change your mind and try to solve these integrals which are used for the Schwinger representation, which might be, of course, much more difficult. But I'm not saying that this is.
Representation too. It's a kernel. Well, some of them can be written as a kernel in quantum mechanics. And it is going to involve infinitely far in the future integrals. And the numerical relatives would say, look, I don't know how to do that.
It's hard problem. Numerically, it's hard problem. No, you're right. Yeah.
So I think
No, but I think there is
also
regarding the number of initial condition of this type of differential equation with infinitely many derivatives. But
it seems to me that if you've got a kernel like that, it's involved asking for information infinitely far in the future and brings it back to the present, no matter how highly you suppress it as highly as you want. As long as it's not zero, it's obvious that the following thing is true. I can get arbitrary time evolution up to some finite time in the future and then pay for it, no matter what time evolution you want. You can have it spell out your name in Morse code. No matter what time evolution you want, you can pay for it by having it be, by having the stuff from the far future come back and make that equation be consistent.
So I would maybe try to.
Sorry, just a comment. So this discussion is very interesting, but if other people have questions, raise your hand such that I can. We can also give the word to others. So for now, you can continue. But if there are other questions, please say that.
So let me maybe try to generalize. I mean, I think you take a very binary statement like some future data contribute or not. There is no way between. But with this non-local form factors, exactly the scale lambda, which Leonardo wrote here in this form factor, plays the role. And for example, we can see in the numerical simulation for not just gravity, you can just take linearized gravity, but still with the form factor, and you look for solutions, you get a solution that looks like a core of the Schwarzschild, but is of course expanded, and the characteristic scale is given by lambda. So what I'm saying is that if I can draw, where is the person? I don't know. So basically, you can have some profile that if you would, no, sorry, I cannot open. Can you help me? Oh, thanks, 2%. So you can have some profile of the solution that basically here you would say it contributes for sure. So this is probability 1 that this initial data are important, but then what you see is that this is a smoothen out, and then finally asymptotically the probability is 0. So I don't.
It's never quite 0. It always has some.
Yeah, but this is a question of support. I agree that support is infinite, but it's not only the support what matters, it's also how important is this.
What I claim to be true, and what I don't think you've addressed yet, is that if I cut off time at some fixed amount, capital T, I claim that whatever evolution you want can be supported by just paying for it, and no matter how highly you suppress it, as long as the future is not 0, I claim that I can adjust the future to make the equation be true from t equals 0 to t equals capital T. And I think that's just obviously true, and I think you should regard that as a problem.
I would say that here, how the future time solutions contribute, it really depends how they are. And then asymptotically, we see that they go to zero. So it's true that support is infinite, but the farther you are, the more suppressed this contribution is. So
Okay, well, I've made my point and you don't accept it, so I think we should.
I mean, I think it's the discussion whether what is important mathematically support or what is the integral. And then, we can have a function which extends to infinity, everywhere is non-zero, but maybe this part of the integral is suppressed. And then the
Again, has
question is
something to
support or the
say
integral.
about that.
No, I think that most of your comments apply to generic non-local theories.
Yes,
These are very specific ones. They have some very magic properties, even from the renormalization point of view. And so you should try and prove your statements in these, which are not generic. They are absolutely special. And we know their speciality more on the quantum field theoretical side, of course. For example, today you asked about e to the box is not a good function. Okay? E to the box. Sorry. Just to say that they are special. E to the box is not in that category.
Oh, okay, good.
But let me show you.
But as long as the kernel has some non-zero support infinitely far in the future, what I claim is that if you go from t equals 0, little t
I heard your claim. I simply do not see
how can you ever
But just let him explain.
if e to the box G mu equals 0. What are the extra solutions? You say box equal infinity, box phi equal infinity.
Yes.
What does it mean? What is phi?
It means that the time evolution becomes
Give me the
infinitely
function
better.
phi equals.
It means that the time evolution becomes
Phi
infinitely
equals
better.
is a mathematical expression. Box phi equal infinity. Don't know what it means.
No,
What is phi?
box phi is equal to 0, excuse me, box phi is equal to minus infinity, yes. And what that means is that phi is oscillating infinitely rapidly.
What is
And I
phi?
claim that that's the right.
Since we had to talk about the space of functions when we consider.
Yeah, so Leonardo wrote
The space of functions.
that is the question that one is.
I just wrote
What is phi?
Well, when you say you're defining a space of functions, you're trying to do
Into the box phi equals 0. What is phi?
well, you're trying to do something that's usually not done in business.
sorry,
You're trying to say that
This is a mathematical question.
I mean, this
Yeah,
is
I
the
mean,
problem,
that is
right?
the
This
question
your
that-
question, right?
the future based on the past.
Is
and
this-
they put some insistence on what the future
$1 million to find it's recorded. So $1 million to who will solve this equation.
You made the bold
I need
statement.
something that's awesome.
I don't want some, I want an expression.
Sine of infinity times t.
Thank this goes a little bit.
More questions on different points.
At a different point. Maybe like, I hope I don't throw up another. About local normalizable theories of gravity. I can totally understand where you come from and that you solve the renormalizability problem. But ideally, for a quantum theory of gravity, you want to insert a standard model, and then folklore, or like one idea is that quantum gravity should also solve some of the problems of the standard model, like triviality or underpose, whatever you want to call it. How does that work in renormalizable or super renormalizable theories? Because, I mean, naive argument would be gravity decouples at high energy, so it cannot improve these behaviors. Do you have any idea?
Well, to me, one possible solution of for example, the Landau pole in the standard model of particle physics is an upgrade of the standard model to a non-local theory. So for me, the new standard model will be this one actually.
Oh. So you also.
But we have to make computations there, which will be, there is a paper with Tiberio, Breno, Gianluca, and Lesla, in which we study really the divergences in this class of theories with only one scalar field theory, but you can introduce all the standard model particles. And we proved that, well, we didn't make computations explicitly, only power counting, but it should be finite theory, and so no Landau pole at least. Other questions maybe are still open problem.
Yeah.
But you have to modify, to me, even the standard model sector.
But I'm not talking about non-local theories. I'm talking about local.
Well, local theory is quite similar argument. You just don't have this crossover part with the exponential and gamma function contribution. Okay, so you can achieve renormalizability, or actually finiteness, but in the higher derivative local theory, here you will have the question of motion of the the standard model, and the form factor will be just a polynomial, not an entire function. That's it. Then there are special polynomials according to the Anselmi-Piva prescription, complex conjugate pairs, whatever theory you like. But in the end, will be finite. And this, but I don't know, other questions about problems of the standard model, maybe I can think later. The Landau pole should not be there anymore, because
I can see that you can fix theory problems, but then you also have to connect to low energies.
Well, the low energy is exactly the same, because the low energy theory at the classical and quantum level is dictated by the spectrum of the theory. So the non-analyticities of the theory, or the log of box or p square, etc., are exactly the same. So you will have a finite quantum effective action when you are below the non-locality or the higher derivative scale. You reproduce exactly all the same results of standard model. Just the simple argument for you could be that you can see the non-locality scale like a cutoff. So since this cutoff is at the denominator of higher derivative operators, when the cutoff goes to infinity, these higher derivative operators play the role of regulators. And then you have to recover the usual results of the local theory. It's like a regularization, if you wish, in that sense.
And do you think, well, don't follow you.
Yeah, so I agree very much with the last point, that we can view, especially in a non-local case, like a regularization, when the presence of lambda is kind of explicit. And yeah, I of course agree with Leonardo, just that let me tell you that we can at least theoretically divide these parts of the problems of the standard model into two parts. Ones which really have to do with the UV, like Landau pole, and this is about RV running. The other are more phenomenological, that maybe you also mentioned, like triviality problem or the hierarchy problem or the naturalness problem. So for this first part, it's kind of easier here because already have a good control over UV. So you can basically, with the choice of appropriate form factor, you can avoid the situation of Landau pole or of any singularity. Actually, you can play with behavior there. For the second part, which are more important problems, I think that, and actually it's one of the, I would say, a drawback of the theory, of all this kind of framework for theories, is that you may find a form of the form factor, even if you select what's the asymptotic behavior. Still, there is infinite freedom how to select the form factor, and probably, although it's of course not proven mathematically, but probably you can pick up a form factor that does the things that you want. So, for example, want to solve this, and when you want a very particular trajectory, a choice of the form factor can let you do this. So it's unfortunately, because it's infinite class. So we open like a Pandora box with infinite number of operators, and from the point of view of being very kind of restrictive and predictive, it's going opposite way. Yeah? So this means that basically, if you allow for everything, then you can have and solve everything. Yeah, so this is basically the statement. Which is, I mean, it is also the future direction that we are thinking here, because it's a very important problem how to determine the form factor. But if there would be one, because of, I don't know, some symmetry principle, then yes, when you would say, okay, this is a check of the theory. You check whether this form factor works or it doesn't work. It's 1 to 0 binary. But since we have infinite number of form factor, it's a drawback that basically to every problem you can cook up a form factor that solves this problem. Eh?
But the theory should tell you which form factors you should pick. And for instance,
yeah,
by requiring the fixed points.
And this is unfortunately, okay, we have few examples. And there was this infamous that already Damiano mentioned. I can say, for example, string field theory. It's not that we all have to love this approach, but string field theory is supposed to give 1. But this is that infamous exponential one. So it was like Alessia, you said that's the more fundamental theory should tell us what's the form factor, but in this particular case, it doesn't work. I mean, if you take exponential form factor, it spoils the normalizability in a sense. So that's why we don't like. And there are also other problems that's why we don't like. But this is one example. So maybe maybe other theory. But I agree with the general idea that the theory should tell you what's the form factor. But one example that we have, it doesn't really go in good
Why
direction.
doesn't it work? Sorry, you are talking about, so that was the thing that comes from string field theory is free vertex, but then the amplitude itself might scale principle differently, right?
Yeah, the amplitude and higher point functions, they could be different. Yeah, but we already, if we buy this framework and we use the form factor, which is determined from string field theory, this is that bad one because it's exponential or exponential of the polynomial. And this doesn't give us a renormalizable theory in the sense of perturbative renormalizability. Because actually we can say that if you remember both in Leonardo and my talk, we showed the power counting analysis. And this was very much based that you, in the UV, reach a polynomial asymptotically. If you take exponential, it's not polynomial. And then I tell you what this means technically, is not that you generate, for example, in 4-dimension R² divergence, but you generate divergences with more derivatives, so R box R. And this is not what you naturally expect. And then you go to higher loops, it grows, without bounds. So, for example, R box R, you generated one loop, R box squared R at 2 loops, and then, it grows. So we basically...
It would still be non-perturbatively.
No, not perturbatively, yes, but at least in the framework that we are presenting here, this has to be rejected because it's a theory which is not renormalizable.
Just that it's probably not useful to think of string field theory given you form factor.
Yeah, this was just to show the idea that Alessia could be right.
Define the way that propagates a standard fold field, because otherwise, if you imagine integrating massive modes, you will not get normal effective action. So this matrix should be well defined. And starting with string field theory, you should define well defined this matrix. So if you put a form factor, you change your sort of standard spec. Even if it's whatever, as you said, exponent is just not very good function.
Sure, I agree.
So, but I think
redefine the field. So if you have infinite number of fields, that's okay. You can just redefine all the fields as long as you're not changing S matrix, and you will not change S matrix.
Yeah, but I think what they were talking about is not inserting a form factor, but there is a derivation. I don't know how stable that is, but there is one derivation showing like the scaling of the free vertex, and that scales as a E2 box something.
Yes.
Yeah.
In the interaction vectors, no, yes.
Yeah, that's what he was talking about.
I think there is a difference between string theory and local theories. In string theory, there is modular invariance, which is the real reason of a finiteness. Here we don't see that kind of symmetry. But the exponential are the remnants of non-locality, because string theory is non-local, of course.
Essentially, how you sum all these infinite set of fields with specific prescription, what you get when you get an integral, which is like for the proper time, something that you need to restrict to a certain region.
Exactly. Yeah, exactly. The modular invariance. So yeah, to me, well, there is the common feature is non-locality, but it's difficult. And to me, this should be a fundamental theory, if you wish, or a class of fundamental theories.
But I think the string theory is different from locality in a sense that it has to do with really extended object.
Yes, it has to do with extended objects. Exactly. Exactly. Because there you start from the string and you get no locality. Here you start from locality. So
I have a kind of naive question. So suppose you believe that there is a gravity with this form factor, and we couple it to matter. And matter better not change what we see at low energy, right? So we know what I mean. The standard mode. Fields have standard propagation. Is it clear that somehow in this, when you couple them, and if you imagine the cutoff is not one, but you have another scale, right, in the exponent, will it not kind of change the
math section, for example, just ask what would be the propagator of the scale.
Well, you have to think that all the internal lines, gravitational internal lines, will make any loop integral very convergent. And then on the base of this, what I expect is still a renormalizable sector.
Of course, you will not change the flow entity. Yes,
that's
kind of.
So if you couple that Lagrangian to the standard model, then the quantum effective action will be, so the gravity sector will take corrections also from matter, but the usual one, R square, R mu square.
No, I was asking about the opposite, so.
The opposite, I don't think, well, I did this computation, I don't remember the outcome, but I don't think you can change, well, the finite contribution, of course, will change, but divergences probably you can do in a way that do not change, but I don't remember exactly this, but it's written somewhere in some notebooks. Yeah.
No, yeah, if I can try to answer this, yeah, I would say that everything here depends on a scale lambda, and since the characteristic scale of the standard model is not the same like the Planck scale, and then typically here the lambda we expect to be of, let's say, related to quantum gravitational origin. So most of the expectation is that this lambda which enters that exponent is mass Planck.
So that's a big if, because there's no good reason, like in string theory, there's no good reason why Newton's constant is related to that a priori.
Yeah, so here a priori, yes, in principle could be also, and then we could have basically, okay, I don't want to call it alpha prime for non-local theories, but this would be like what's the coefficient between lambda and mass of the Planck, yes.
Another fundamental scale of how they are related.
So at least there is a property of this theory, and that's what is actually explicitly visible from this formula, that if you take energies which are much smaller than lambda, and you go, for example, to momentum space, all these Lagrangians, when you expand to the first order, they produce you just the terms that were quadratic, so they are exactly like in the standard model. And when the first correction, this scales like energy square over scale of non-locality square. Yeah. So if this scale of non-localities is much higher than the scale of the standard model, I expect that these corrections are sufficiently small.
Damiano wants to comment on that.
No,
New topic. Okay. But wait, is it a follow-up or?
Please. No.
Okay.
I mean, you know that the string effective action, when you make you have R plus all the
Riemann derivation, for example.
Yeah, you can expand also your action. It's your action a subset of terms that you find in string theory or not?
Well, in string effective action, you will not include these two box terms in your propagator, because you will say, okay, I know this matrix, I reconstruct effective action.
No, but
and you can redefine them.
But the effective action, there is no the Lambertian in the propagator.
Yes, that's what I'm saying. Yes. Well.
So I remember there is a
you
paper.
Divide by, you have this exponential -1 divided by
This one, you mean? So this operator is everything. There is no other term. In string theory, usually you have an infinite number of operators. And what people did in the past to show that there are no ghosts or utilitarian issues in the effective theory, what they did is to make a field redefinition to remove all such operators. But in that case, you can do, because you have an infinite series of either derivative operators with Riemann cube, Riemann to any order. Here you can't, because that's the whole theory, no? You cannot. Well, but actually, if you field redefine, classical is equivalent to unfinished.
Each term, the D'Alembertian is always upstairs. There is no D'Alembertian downstairs.
But you can expand. You can expand about.
Yes, it's box plus box. Yeah.
If you expand.
So if you expand, this is the sum of from 0 to infinity of box to n.
Yeah. But then if you expand, also in string theory, you get an expansion.
Yeah.
Oh.
Now, can you identify the terms in the two expansion?
Well, if you have the string effective action written like you said right now, we can compare some operators, yes.
But that's not good as me. Here you will change property. If I correctly will not include this.
Yeah, that's what we do.
Yeah, I think that Paulo and Arkady here, you are perfectly right that in string effective action, the propagator still scales like 1/k². Because of this argument of redefinition. And then, for example, one term that, okay, we do not expect because we are not working in 6 dimensions, although we could, is that in string effective action, you get this Gauss-Bonnet, which in 6 dimension doesn't, is not the topological, but doesn't influence the propagator. It starts as a vertex, as a free vertex. So this is the Gauss-Bonnet term. And others, which are in this series, they are kind of higher than that Gauss-Bonnet. We don't include, here. So all we do is terms which are quadratic with form factors that they modify the propagator. And even if you start with higher derivatives, it is not a propagator 1/k². It is at least 1/k4 or higher powers.
Yeah.
In the string effective action, there is no propagator.
Yes.
When you write R plus R squared. Plus
Yeah, but we can
But
have.
I mean, you can.
Yeah, as squared you can
Can-
Yeah, usually the
Chase says that Chase follow up. Okay, I mean, at low energies, the parameterization of the effective action should match in the sense that in general, you can have all of this tower of operators. In some theories, many of them will be just 0. In string theory, you would expect that these operators, the higher reliable operators, are all related to alpha prime. In general theories, like in quantum field theories, not. I mean, there can be different coefficients. But if you go already above the string scale, you would presumably see differences. There you see no localities, which you don't have in string theory. But at the same time, in string theory, you would have the E2 box, so the dilaton that multiplies all of these higher derivative terms. And that's also an additional difference that you don't see at low energies, but you see at high energies. So yeah, at low energies, you can kind of compare, but above the string scale or close to the Planck scale.
Moreover, in
It's
string theory, there are
difficult.
infinite number of resonances. Here, there is only the graviton here.
Yeah.
Around Minkowski. So that's a crucial difference.
But in string like Gauss-Bonnet, there is an exponential dilaton. So it's not.
There are other parts. Yeah,
Yes.
for example, as a mass, there are more.
And other modes, yes, but the dilaton really multiplies everything, so it's kind of important in this comparison. Damiano had a new point.
My point is about formal things, because I understand that it is fashionable to put formality everywhere, but in 4 dimensions, the conformal dividing variant theory has infinite properties of shape in time and dynamics. So how do you define any theory? 2 dimensions, for example, you have a scalar field in 2 dimensions, you have the same problems, but they are treated in primary fields in a completely different approach. I don't think there is any analog in 4 dimensions. So when you talk about supergravity, you by supergravity or by gravity, how do you define it diagrammatically?
Me, I don't know. This is a question for Mannheim, maybe, or for you. But I understand the point. It's 1/v to the 4.
Square are things that I cannot even define with my own prescription. These I cannot reach. 1 divided by box square, I don't know how to.
So I would say that
There were some discussions, I think, and you can formally consider the scalar theory with box square. So it's indeed a close analogy to the dimension.
You can.
And then you need to consider exponential operators. That's exactly the same as in 2 dimensions. So you need to consider.
Some prime.
Yes, so your scalar has 0 dimension. Then you consider exponent phi and their correlation. Okay. But indeed, scattering phi is just like scattering mass by scalar. That's okay.
yeah, so it's true that there is this infrared problem, and that's why, for example, we cannot define well the scattering matrix. And I agree that there is one part which is a theoretical discussion, and whether we want to take really this conformal wide gravity as a theory which is working at all the energy scale. But for me, and this was some kind of part of motivation, I wanted to use it only in the UV. So the question could be how I can relate this theory to some valid theory in the IR. And in the first part of my talk, I used the conformal invariance not as a fully fledged theory that is working all the energy scale. It's just that I needed it in the UV, and I have a very particular reasons because yeah, I think that this has very high chances to be really the solution for the problem of singularity. I mean, without other symmetries, singularities of general activity, I don't think that can be so easily resolved. I think maybe you Leonardo, can add something on this point.
Yeah, but the question by Damiano was really peculiar for this kind of theory like by gravity, because you have this propagator 1 over p to the fourth, so you have bad infrared divergences, but I'm not familiar with, it seems that if you consider other correlators, they are well defined, but this is something. And well, I don't know.
Yeah, it would be like I said, the theory in the UV is like the theory of gluons, and when we know that in the IR there should be somehow mesons.
No, I think this is much worse.
Yeah, this
Much-
is much worse. Yeah,
You know what,
much more
because
complicated.
Damiano is worrying about the following thing. Usually, with theories in which you have higher derivative but the mass scale, you can implement the AP prescription, this Anselmi-Piva prescription. Because you don't have infrared divergences. You have box square plus m to the fourth. So no infrared divergences. When the energy goes to 0, there is the mass, which is the cutoff. So what you can do, but if you don't have the mass, you have to cancel infrared divergences with soft particles, soft energy. So I mean, however, in this prescription, you don't have such contributions because they cannot be on shell. Therefore, you cannot cancel infrared divergences coming from loop diagrams. That's as far as I understand the issue. Yeah. Yeah.
Any other question?
Yeah, maybe just a short follow-up. I mean, it could be like a question. I mean, it's a valid question, but how to define the limit? And if the limit can help anything here, because maybe we can try to send the mass to 0, but you have to do this in a very delicate way, and probably just naive way will not work. Yeah?
Discussed last week, why should the theory have a nice ultraviolet limit? If it doesn't, it's okay. I think that these theories do not have a nice ultraviolet limit. Nice, asymptotically free, asymptotically safe, I don't know, so on. But as long as your Einstein curve is there, you are not treating the conformal limit, you will have a natural cutoff, which is the Planck scale. Because it is there. You don't have but if you want to push it to discuss what is the ultraviolet limit of this quantum field theories, I don't think it is anything nice, and I don't think this is a problem.
I can comment on that. I mean, I don't care about infinite energy as a thing, because infinite energy we will never reach. But the point of having asymptotic freedom or asymptotic safety is that ensures predictivity. So you know, and based on the characteristics, on the features of the fixed point, you can precisely say how many free parameters you have. And if
that's the requirement you make to have predictivity there. But they can have predictivity in other approaches like quantum field theory from low energies and reaching whatever I can reach perturbative, typically the Planck scale.
But that is related. I mean, it is related to a number of relevant directions that you have. And if you have a perturbative normalizability, typically you have a finite number of constants that you have to set.
I think you don't discard PV because you don't know the ultraviolet limit. It's beyond the perturbative region.
Yes, but that is going to, I mean, we know that there is more. And it's not about infinity, it's about finite scale, of course. More follow-up or questions? Okay, so if not, I think it's a good point to close the open discussion. So thanks again to Leonardo and Laszlo. And yeah.